Hey students, I'm Rudi Schlaf. I'm a professor at the Electrical Engineering Department at USF. I developed this course in 2010, and the main reason that I did that is that back then global warming became a big topic in the news, and I got really interested in the scientific and reasons behind that and the technologies that we could use to try to avert it. Other reasons why this is an interesting topic is fracking. Also, the energy demand in developing countries is going up rapidly, and so we have to come up with something to provide this energy. It doesn't appear very feasible to simply pump more oil out of the ground. Um, so I decided to teach this course, and I think the main purpose of this course is to explore the scientific backgrounds and to understand the risks and benefits of sustainable energy technologies and the competing conventional energy technologies. I'm hoping that this course will help you to become more knowledgeable and to be able to contribute and participate in the public discussion about this topic. It's pretty obvious that there are many irrational ideas floating around out there, and I believe if people would know more about the scientific underpinnings of all this, then I think the discussion could be much more rational and focused. So let's get started with a list of reasons why it might be interesting to look into sustainable energy technologies.
Even if you're not concerned about climate change or pollution or such issues, there is no doubt that fossil fuels are a finite resource. And if you consider that most of our economy directly depends on the availability of cheap fossil fuels, just think of transportation, electricity, heating, cooling, even fertilizer, everything depends on fossil fuels. And so imagine if we would suffer a major disruption of fossil fuel supplies, then it would cause major economic issues. And such problems could occur on a timescale of years to a few decades. Right? This is all published from by the Department of Energy, and there's also a very famous paper by Hirsch. Um, of course, also once we run out of fossil fuels, prices are likely to go up since there is increasing demand and it gets more and more difficult to retrieve the fuels. So that would mean significant price increases. In fact, I think we already saw this in the last few years. Right, gasoline costs right now close to $4. 10 years back, it was at about 99 cents. And one of the main reasons for that is that in developing nations, more and more demand for fossil fuels occurs, while it gets more difficult to find it. Think of fracking and all the other unconventional fossil fuel sources that we're now increasingly accessing. Another issue is the security of energy supply. Right, a large amount of the world's fossil fuel resources are located in problematic areas that are politically unstable or difficult to get to. Think of the the Arctic region, for example, or deep sea drilling. Then, of course, there is the pollution issue, right? Even before the discussion about climate change started, pollution causes a large number of cancers every year. Each coal-fired power plant releases a whole bunch of radioactive elements. In fact, it's much more radioactive around a coal-fired power plant than around a properly working nuclear power plant. Then, if you remember a couple decades or three back, acid rain was a big deal, right? Because there's sulfur dioxide that comes from coal burning. There's a large number of particulates in the exhaust from fossil fuel burn, and even if it doesn't cause lung cancer, there are a whole number of respiratory illnesses that are caused by this. So the bottom line is that burning fossil fuels is pretty dirty, and if we want to do it safely, we have to go through quite an effort to clean up the exhaust gases. If you think that climate change is an important factor, then of course you need to consider the large amount of carbon dioxide that's being emitted while burning fossil fuels. Anything that contains carbon, right, when it reacts with oxygen, makes carbon dioxide. And so this gas is suspected of causing the greenhouse effect. A very interesting point is the energy return on investment, in short EROI, deterioration. As it gets more difficult to get to the fuel, you can also see that it is becoming more energy intense to get to that, and that means that a larger percentage of the energy that is extracted is actually being used again to extract more, and so less and less of the energy that is being found goes towards uses by society, right? And more is being fed back into the energy finding process. Last but probably not least, sustainable energy technologies are typically more advanced than conventional energy technologies, and so what that means is that there are usually better jobs associated and also cleaner jobs associated with sustainable energies. Think of installing or developing wind turbines in comparison to digging a mine and going underground for 1,000 meters to hammer coal out of a mountain. So all of these reasons are pretty convincing, in my opinion, that sustainable energy is a very interesting topic to engage in, and that it may be a good idea to try to reduce fossil fuel burn in the near future. So before I go over the chapters of the course, let's have a look at the US energy flow. So this is a really interesting a graph that is being put out annually by the Lawrence Livermore National Laboratory. And what it shows here is the energy inputs and then the energy conversions that we're going through in our society. And it's actually interesting to point out here that energy cannot be consumed, we can only convert it. So the energy sources that we put into the system, oil, coal, natural gas, nuclear, hydro, biomass, these energies, these are basically storage forms of energy, and when we convert the energy from these storages to energies that we use, that is of course electricity, that is heat, that is kinetic energy if you think of cars and so forth. So we go through conversions, and these conversions are basically shown here. And so we put the oil into the system, and then we convert it to gasoline in the process here, and then we put it in a car, and it becomes transportation fuel. And in the car then, what happens is, you are probably aware that there's a lot of heat generated. That's why we have the big radiators under the hoods. And so this is the energy that is lost, and then we also get a little bit of kinetic energy. That's what actually moves the car. And so you see here that this conversion process, by going from the energy stored in as chemical energy in the oil to kinetic energy, causes a big deal of heat release, and this heat is essentially lost. This is an unfortunate fact. We cannot really get around this loss, because every time we convert heat to some more a higher quality energy form like kinetic energy or electricity, then we always lose a large part of it in heat. We will discuss this more in the thermodynamics chapter, why this is occurring. Other examples for conversions are, for example, if we look at natural gas, it's being fed here into the residential and commercial sectors. And of course, a lot of this gas is just being burnt to create heat. But then some natural gas is used to generate electricity together with coal. These are the two main sources in our country to make electricity. Some base load is covered by nuclear. But you see here also, as soon as we make electricity out of these stored energy forms, then again we have a big loss, right? Most of it is actually lost at heat. This is why we have these big cooling towers next to major electrical power plants. And a much smaller amount here is actually being converted into electricity, which goes into the grid. And so some of this electricity is used in residential and commercial settings. And then, of course, when you use it in a stove, for example, then you generate heat again. And so of these inputs, again, we're losing some through the conversion process, right? For example, if you turn on your TV, you may have noticed that it gets warm. And so we put electricity into the TV, and then we get some lost energy. This is the heat that comes out of the thing. And useful energy is actually that it produces an image that you can look at and receives the TV station signal and so forth. Okay, so every time we convert, we always generate heat, and that's lost, and then we get a certain amount of the energy that was useful. But in the end, keep in mind that whatever we do here, we always end up with heat at the end. So if you think of a car, you may accelerate it with this little bit of kinetic energy that we squeeze out of the oil, but then when you bring the car to a stop, then of course you heated up the brakes, and so all the kinetic energy is converted to heat. So in the end, all of these inputs are essentially converted to heat. Okay, so let's look at the numbers here real quick. It says here that the net primary resource consumption is 97 quads per year. So these are the primary resources, and the energy that's contained in them is 97 quads. So what is a quad? One quad, I looked up, is a quadrillion BTU, which is 293 billion kilowatt hours, and we can also say that is 293 terawatt hours. So this is one quad, and so we are using almost 100, and so that then turns into petawatt hours. And so in 2012, this number was 95.1 quads, and so that converts to 27.8 petawatt hours. So if we divide this here by the hours that we have in a year, because this is the annual consumption, then we can actually calculate what is the power of the energy supply that we need for our country in a total. And so the power need that we have, and I really shouldn't have written consumption here, is 3.17 terawatts. So you can divide this number you get by dividing 27.8 petawatt hours by the number of hours in a year. Just to give you a sense of the magnitude of this wattage, a major power station, major nuclear power station, or really big coal-fired power plant has about 1 gigawatt. And so if you think that we are basically wasting 2/3 of the energy to heat when we generate electricity, this here would correspond to about 1 terawatt generation power, and so this is the equivalent of 1,000 of such power stations. So pretty amazing amount of energy that is going into this system. It's interesting to look real quick at the 2012 update to this graph. You see it here. The major changes are that solar and geothermal and wind are on there, but we stopped apparently importing petroleum. And on the other end, the interesting thing that happened is that energy services now stands for useful energy, and rejected energy stands for previously lost energy. So one can only wonder why they made these changes. Before I talk about the segments of the course, one more slide that is important for the entire course. An important way to assess the usefulness of an energy source is to look at the energy return on investment, the EROI. We will use this throughout the course. So the EROI, that is essentially the ratio between the energy produced and the energy invested to get that energy that we produced. Currently, if you look at oil coming from Saudi Arabia, for example, where it's fairly easy to extract it from the oil wells, we have an EROI of about 18 or so. That varies, of course, from oil field to oil field. But if we have an EROI of 18, then what it means is that if we get an amount of 106 of energy, then 100 of that would go to society, and this little bit here, 6, would have to be fed into the extraction process. So this would be the energy to drive the trucks and oil rigs and pumps and all these things that are involved when it comes to getting the oil out of the ground. So at 18 it seems pretty reasonable. Society gets most of it, so we can put that in our cars and heat houses, etc. Now if we go to lower EROIs, so if we have an EROI of 1, that means we don't get anything anymore. And so corn ethanol has an EROI that is pretty close to 1. In fact, if the EROI gets smaller than 1, then actually we put in more energy than we get out. Certainly not something useful to do. And there are actually some scientists that think that corn ethanol is even below 1. Now, if we have an EROI of 2, that means we lose 50%. There is some evidence that the Canadian tar sands resources are pretty close to 2. There may be 3, but a large amount of the energy needs to be reinvested into refining this tar and getting it separated from the sand. So essentially that means one has to heat it up, liquefy it. So a lot of energy is going into that. So a source like this has an EROI of 2. And so what happens there is when you have a low EROI, then you see here that of the extracted amount of energy, most of it we're feeding back into the extraction process, and society only gets very little. So if we wanted to get the same 100 units of energy for use in cars and so on, at an EROI of 1.2, we would have to produce actually 6 times this amount of energy in order to get this little bit of energy into use in the society. So most of it is actually being fed back. So at an EROI of 2, this and this would be the same size. So we would have to extract 200 units for every 100 units that go to society. So it's immediately clear, the lower the EROI, the more effort we need to put into getting the energy, and less of the energy is going into society. So if you look at current conventional oil resources, so these are not the tar sands and not fracking, etc., they have an EROI of 15 to 20. In fact, when oil was first discovered as a convenient oil source in the 1910s or 20s of the last century, this EROI was close to 100, and then over time, because the low-hanging fruit is always plucked first, this EROI dropped more and more, and it's currently at 15 to 20. Now we can expect with more and more exploitation of unconventional oil, this EROI will go down further over time. So this means that oil will also get more expensive because of this. It's pretty obvious, right? If you lose most of it, then what you can sell here is becoming more expensive. It's interesting to look at what wind and solar has as EROI. And so wind is pretty similar to the current oil resources. But if you look at silicon solar cells, which are the bulk of the solar cells that are currently used, they, depending on how they are made, they may have only an EROI between 5 and 10. So this is not so great. So a 5 would mean that 1 out of 5 solar cells would have to be used to actually generate the energy to make the other solar cells. Okay, so it's clear that if we want a good benefit to society, we need a large EROI. That's one of the challenges with sustainable energy.
Okay, now it's time to go and look at the course overview. This slide here shows the chapters of the course. So we'll begin with reviewing carbon-based energy, because that's what we're having right now, what we're using. And so we will discuss where oil is coming from. We will discuss greenhouse gases, global warming, pollution, this kind of thing. And then we will go into things like fracking.
Here you see a schematic of the fracking process. So what you do is drill a hole, and then there is lateral drilling. That was the great invention that led to fracking. So they can actually drill around the corner now and go into these shale formations that are filled with gas. And once you have this this hole, then they pump in water mixed with some chemicals under high pressure, and that cracks the rock around as well. And that releases the gas that is in this shale formation. So that's great, right? So we get the gas out, but there are also other issues, because we pump in all these chemicals, and these chemicals, they can leak into the groundwater. There are also reports of small earthquakes that are being induced by this process. So there are some, like with any large-scale technology, there are some issues when it comes to environmental compatibility and so forth. So this will be one of the things that we will discuss in the carbon energy chapter. The next topic is a brief overview over energy-related physics. And here we will talk mainly about thermodynamics. Probably the most important topic in that chapter is heat engines and why they have to lose energy. So in a heat engine, you always take some high temperature energy. So that might be the explosion in a combustion chamber in your car engine. And that is then converted in part to mechanical labor. So that's what drives the drive shaft and moves your car forward. But then also we have to discharge energy into a lower temperature environment, the low temperature sink. So this would be what's coming out of your car radiator up front. And there is just no way around it. There is no way to convert this here also to labor. And so we have to live with this loss. So we will explore in this chapter why we have to do this. In the next chapter, we will review transportation-related energy use as the major example for energy use in our country. And here we will discuss the various methods of transportation that we're using, and how much energy each of them costs per distance and per weight transported and so forth. Then after we discuss energy use, we will finally go into energy sources and energy storage. And so we will discuss solar energy. Their interesting topics are the various types of solar cells and the EROI. Here on this slide you see the various steps that are needed to make solar cell grade silicon wafers, and it becomes immediately clear why the EROI of silicon solar cells is not so great, because there is a lot of energy going into it. As you probably know, when you make silicon wafers, you start out with sand, which is silicon oxide, and so we have to remove the oxygen, And that means we need to put all that energy back into the silicon that came out when it oxidized in the first place. And so the initial step is to actually use coke and make carbon dioxide, and then in an arc furnace, and in this process we get pure silicone. And that then goes through several more steps, some of which cost a lot of energy, until we have finally clean, high-grade silicone that can be cut into wafers and then be put in a solar cell. So this is one of the interesting topics about solar cells: which ones have better or worse EROI. So this is the type of thing that we will discuss in the solar cell chapter. Then we will discuss wind energy. It's pretty interesting to know that in the US we have a lot of wind. This here shows a map of wind in the United States, and if you look at this color code here, these are the wind speeds that we're having, and it's immediately obvious that the higher wind speeds that are suitable for efficient use of wind turbines can be found all over the Midwest. And of course that's a great combination, because there are also not so many people live here, so there are large areas where we can put up wind turbines that don't interfere much with populated areas. Also, wind turbines get along well with agriculture, and so this appears to be a really nice combination. Then the next chapter is bioenergy. And there, one of the big topics to look at is the EROI again. How much energy does it cost to produce the plants, and how much energy do we get out from the fuel that we can produce from them? This slide gives some good idea why plants are fairly poor energy conversion devices. Here one can estimate that the rate of energy storage by land biomass, so in all the plants that are growing, is 95 terawatts. So this is energy stored per time. And so if we compare that with the primary energy consumption on the planet, which was 14.3 terawatts, we see that the rate at which energy is stored in plants is only a factor 6 or 7 that of the power that we are using. And this means that we would have to use a very significant part of all the plants that are growing on the land area of the Earth if we wanted to come up with enough biomass related power to cover this power need. What we also see is the rate of energy storage, 95 terawatts, is very much smaller than the power that is reaching the Earth emitted by the sun. So that is 174,000 terawatts. So if you do the numbers here, this shows you that only 0.05% of that sun power that is reaching the Earth is converted actually into biomass. So this here tells us that plants are very, very inefficient when it comes to converting energy from the light into biomass that we then can burn and make electricity from, and so forth. After covering energy sources, we will discuss energy storage. And so the first topic is hydro storage, which is the only storage technology that is really widely used. Then we go into electrochemical storage. This is mainly about batteries. Think lithium-ion batteries. You may think of lithium-ion batteries as great batteries that have a high energy density that make your laptop run much longer than on the old nickel hydride batteries or something of that type. But if you look at this graph here from Wikipedia, which shows the energy density of certain energy storage types, then we see that the lithium-ion battery here is nearly at the origin. So on this axis we have energy per weight, and here we have energy per volume. And so if we compare that with gasoline, for example, or diesel, right, what we use in cars, we have a much, much higher energy density than in a lithium-ion battery. And that explains immediately why a electrical car, its weight, most of it almost is the battery if you want to have any sizable range. And so there is a big challenge in making better batteries that get closer to liquid fossil fuels. Imagine if you wanted to make an airplane that has a high capacity to transport loads, then you could not do this with lithium-ion batteries, right? At this point, an airplane that is electrical, most of its payload is its battery. It's very difficult actually to make airplanes that fly purely electrical with battery power. So this is one of the major topics when it comes to electrochemical energy storage. After electrochemical storage, we will also discuss mechanical storage. This is mainly about flywheels. It's pretty interesting. There are actually some satellites that have flywheel-based batteries. And then at the end, we will talk about nuclear energy. Some people think of nuclear energy as a sustainable energy type. However, since it uses a fuel that has a finite resource size, it's much more like carbon-based energy. The various estimates, how much uranium there still is, it ranges from 30 to 100 years or so. But no question that nuclear energy, especially if expanded greatly, would last for a very long time. And then, of course, as recent history shows, there are also other issues with nuclear energy. These issues are mainly safety and disposal of the spent fuel rods. If you remember, about 28 years ago, there was the accident in Chernobyl. And after that happened, they put a lot of concrete on the exploded reactor. And so now after 28 years, they realized that the concrete had deteriorated and that there needs to be a better solution. And so there was just a great article in the New York Times capping a catastrophe. And so here's an impressive picture. They're building the stainless steel arch that then, because the radiation is still very high back there, you see actually here they built this this wall to protect the workers down here from the radiation that is coming line of sight from the cracked reactor block 28 years after the accident. And so this gigantic arch here, this is only half of it, the other half will be built once this here is being slid across on Teflon pads apparently here. So imagine that. So this entire contraption is estimated to cost close to $2 billion. And so if you add in these costs to nuclear power, then of course the question is that still feasible in terms of cost benefit? Of course, other issues are that the entire area here around this plant is uninhabitable and all the people had to move away, etc. So all this puts big question marks around nuclear energy. While it works, it's pretty good, right? No carbon dioxide is being emitted, and it's also a very clean source. It's much better to live next to a nuclear power plant than next to a coal-fired power plant in terms of radiation, which is sort of a funny little bit of information. But anyway, so these things we will discuss in the nuclear energy chapter after discussing how it works and where the energy is coming from.
This concludes the introduction to the Sustainable Energy course. I hope you enjoyed it. Thanks for watching.